delighted to see so many people in the audience today, and I'm even more delighted to introduce Pierre-Emmanuel Caprace from the Université Catholique de Louvain, who's going to tell us about hyperbolic generalized triangle groups, property T, and finite simple quotients.
Thank you very much, Kaluba. Thank you all for being here. It's a pleasure for me to give this talk and to be involved in this program at INI. I think I feel it's a very special talk for me in several ways. The first one is that what I have to say, what I will speak about relates to the work of various people in the audience, which is very nice. The second reason why it's special is because a lot of my involvement in this project was largely motivated by a question that arose 3 years ago when I was attending another special program at INI, which was on geometry group theory, and I will come back to this. And finally, and more importantly, it's a very special talk for me because it's the first day of a lobbying campaign that I'm launching. And the goal of this campaign is to try to convince my friends and colleagues with an expertise in finite group theory to help resolving some of the disturbing problems that geometry group theories have. Okay. And more precisely, I hope that I will explain that better in my talk, but more precisely, my hope is that the expertise that some of you developed in studying the finite simple quotients of triangle groups can be extended or adapted to study finite simple quotients of generalized triangle groups, and that would be very exciting for the geometry group theories. Okay, so all the new bits of my story belong to the joint work with these three guys, Marston Conder, Marek Kaluba, and Stefan Witzel. Yeah, and let's start with this long-standing open problem. So we don't know whether all hyperbolic groups are residually finite. So let me first spend a few minutes to explain why I believe that this is a very important question. So Gromov, in his seminal monograph on hyperbolic groups, so he wrote a remark there where he said probably generic word hyperbolic groups admit no sequences of subgroups of finite index with trivial intersection. Right? So according to this remark, I think we can conclude that Gromov did not believe that the answer to this problem was positive. But still, I mean, okay, this is approved by intimidation, this problem. This problem is important. No, the word, let me insist on the word generic. So one of Gromov's motivation to promote the study of hyperbolic groups is because Gromov was interested in generic properties of finitely presented groups. And Gromov and others developed a probabilistic framework that would give a precise meaning to what a generic finitely presented group is. And in all of these models, almost surely a generic finitely presented group is infinite hyperbolic. So if you believe in that, then my problem about residual finiteness of hyperbolic groups can be rephrased as follows. Is a generic finitely presented group faithfully approximated by its finite quotients, right? And if I phrase it in that way, I think that it sounds like a very fundamental question. And also, if I phrase it in that way, it sounds unlikely that the answer is positive. Now let me give you a second motivation that's completely different. It's a purely algebraic motivation. So one of the first deep results, well, one of the deep results about the algebraic structure of hyperbolic group is a theorem that was suggested by Gromov and proved independently by Kazhdan and Olshanskii in the 90s. So it says that every non-elementary hyperbolic group has this property that we call SQ universality. It says that every countable group embeds in a quotient of G. So really, hyperbolic groups have a huge amount of infinite quotients. In fact, qualitatively, they have as many infinite quotients as a free group of rank 2. That's a way to think about this. But if hyperbolic groups have so many infinite quotients, it's kind of natural to ask about their finite quotient. And it's very embarrassing to admit that we don't know the answer. So do hyperbolic groups, does every hyperbolic group admit at least one non-trivial finite quotient? We don't know, and in fact, this question happens to be equivalent to the initial one by results of Olshanskii and Katowice-White. But perhaps if I present the problem in that way, now maybe one is tempted to believe that, after all, the answer is positive. And I'm not sure there is a very large consensus among geometry group theorists about what the answer to this problem is. But for today, I will propose a completely different problem a priori. So, and in order to phrase this, let me define SD to be the class of finite simple groups containing the alternating group of degree D. So this is my definition of a finite simple group that's roughly of rank at least D. Do you buy this? Yes. And a bit later in my talk, I will put on the board the definition of a group that I want to call G7. And my question is it true that G7 admits a quotient in SD for every D, every D? And if you manage to prove that it's not the case, so if this group G7 does not admit finite simple quotients of arbitrarily large rank, then it will follow that there exists a non-residually finite hyperbolic group. So let me spend a couple of minutes explaining this implication. And this comes from a result of Olshanskii again, that I call the common quotient theorem. So Olshanskii proved the following result that's here. So any two non-elementary hyperbolic groups, G1, G2, have a common quotient Q that is itself non-elementary hyperbolic. So how does that relate to what I said before? So let's apply this result as follows. We take G1 to be your favorite non-elementary hyperbolic group. And now for G2, you take a very special hyperbolic group. It's a virtually free group, the free product of two copies of alt D. Okay. And now let's think about this common quotient Q afforded by Olshanskii's theorem. Let's assume that this Q is residually finite. If it's residually finite, in particular, it has a non-trivial finite quotient. Let's take the smallest one. It will be a finite simple group. But it's a quotient of G2, and G2 is perfect if I take D at least 5. So this finite simple quotient is a non-abelian finite simple quotient, and it's a simple quotient that must contain alt D. So this finite simple quotient of Q is in SD, but Q is also a quotient of G1. So G1 itself has a quotient. Fine, so what we see is that Olshanskii's theorem implies this claim that if all hyperbolic groups are residually finite, then every non-elementary hyperbolic group has a quotient in SD for all D. So this is really what I want to take as the main ingredient to transform my question, my initial question, in another question. I will give you a specific example of a hyperbolic group, and I will ask you, can you decide whether this hyperbolic group has finite simple quotients of arbitrarily large rank or not? Of course, there is a caveat, and you might complain that perhaps I've transformed an easy question in a very difficult one, and I want to emphasize this by reminding Hingman's famous conjecture that he formulated in the late 60s. And Hickman wanted to know whether non-elementary Fuchsian groups admit alternating quotients in almost all degrees. And it took quite a long time. And the work of various people, not all of them are listed here, but the final bits were obtained by Brian Everett and Lilia Ksharev. And there is another related conjecture, more recent, formulated by Jean-Luc Jones in 2013. And they asked the same question not for non-elementary Fuchsian groups, but for free amalgamated products of finite groups. You take you put the obvious condition ensuring that this is a non-elementary hyperbolic group. And at this point, obviously, this is a virtually free group, hence residually finite, but we don't know whether it has half D quotients or almost all D. We only know the case where the amalgamated subgroup is trivial. In that case, it's a result by Tambourine. So I am aware of the fact that some groups are easily proven to be residually finite, but we don't know about their finite simple images of large rank. But remember, in the question that I want to suggest, we don't want to prove that a hyperbolic group does map onto all these groups. We want to prove that it does not. And, okay, so. So my title had this reference to property T, and I want to also spend a couple of minutes about that. So for simplicity, I will define property T not in the original way that Kazhdan introduced it, but by an equivalent formulation, which is a fixed point property. A countable group has property T if any time it acts by affine isometries on a Hilbert space, it has a fixed point. Okay? So finite groups have this property because a finite subset of the Hilbert space has a canonical barycenter. Kazhdan proved that SLDZ for the athlete 3 has property T, and much more recently you had drastic improvement of the statement for SLDZ. You have these groups of elementary matrices with coefficients in the free associative non-commutative ring are generated. So this is an example of a group with a property T by deep result of Hershov-Heiking. So why is the statement about this one much stronger? Well, it's because property T passes to quotient. It's a fixed point property. So if a group has this fixed point property, all of its quotients obviously has the same fixed point property. So if you take a group like this, it has a tremendous amount of quotients. In particular, it has SLDZ as a quotient. So establishing property T for a group that has a tremendous amount of quotients, it's a strong theorem. It's a stronger theorem than for a group that has all its proper quotients finite, like I said. Okay, 3 years ago, so I was here at INI. A program on geometric group theory was organized by Alessandra Iozzi, Cornelia Totu, and Gulnara Arjantseva. And Cornelia asked me, can you find a short presentation of an infinite hyperbolic group that has Kazhdan's property? Why was she interested in this? So of course it was well known, it's known since the work of Kazhdan in the 70s, that hyperbolic groups with property T do exist. The problem here was to find some explicit example, and the question contains the term short presentation. So I asked Cornelia, what do you mean by a short presentation? And her answer was, well, I don't know, something you can write on the blackboard. So what's the motivation to find such explicit examples? Again, there is a generic motivation and an algebraic motivation. So a generic motivation comes from the same reason as before. In some probabilistic models, finitely presented groups are all infinite hyperbolic with property T. So if this property is kind of generic, it's kind of natural to ask for, give me an example. And in the book that Cornelia wrote together with Misha Kapovic in 2018, they wrote this: while generic finitely presented groups are infinite and satisfy property T, finding explicit and reasonably short presentations presents a bit of a challenge. Let me also give you what I consider as an algebraic motivation. So property T yields various very strong consequences for the structure of the group and the representation theory of the group. So one of them is that every finite index subgroup of G has a finite abelianization. This is a very, very strong property. And if you give me a finitely presented group and you ask me to show that it has this property about finite abelianization of all finite index subgroups, I mean, I don't know criteria that will ensure this except property T, although the two properties are not equivalent. Another consequence of property T is that the group has finitely many unitary representations in every finite dimension n. That's an old result of 1. And this has been drastically improved by Rapinchuk more recently. I will not go into that. And more importantly for our question, so property T is incompatible with the existence of codimension 1 subgroups, and I will not go into this, but the existence of a codimension 1 subgroup implies the existence of an action of what we call a Cat0 cube complex. And there was a big breakthrough by Jan Edel and relying also on work of Danny Wise and Frederic Laglum that if a hyperbolic group acts co-compactly and properly on a Cat0 cube complex, then it's residually finite. So staying away from groups acting on Cat0 cube complexes is kind of a desirable property if you want to find non-residually finite groups in this story. So that's why property T is relevant. But if I may make a speculative assertion here, it's my understanding that property T is correlated with restrictions on finite quotients, and hence, if a hyperbolic group has property T, it's more likely to have a smaller amount of finite quotients, and in particular finite simple quotients. Okay, so after hard work, motivated by Cornelia's question, I came up with this wonderful presentation of an infinite hyperbolic group with property T. So I published it because it fits on a blackboard, and in that sense, it answers Cornelia's question. But I must admit that my definition of a short presentation is different from Cornelia's. My definition of a short presentation, it's a presentation that if you look at it long enough, you will not forget it. Clearly, this theorem fails to answer Cornelia's question. Okay, so today's example yields, in particular, an improvement on that result. So now I will show you a presentation, a family of presentations indexed by odd primes of infinite hyperbolic groups, and all of them will have property T if the prime is at least 7, and the presentation looks like this. It's 3 generators. They have order P, and then you have a bunch of relators that are commutators. What you see is that all the relators involve only pairs of generators, 2 generators at a time, not more. Okay, and if you plug p equals 7, and you simplify a bit the presentation, then the total length of the relators is 87. So that's significantly shorter. Okay, so that's G7. That's the group for which I want to repeat the question that I asked before. So does this group admit finite simple quotients of arbitrarily large rank? And the average version of that is, does this group map onto alt D for infinitely many Ds? And again, so the reason why I'm now starting this lobbying campaign with that group, and the reason why I did not start this lobbying campaign with that group, it's not because this has a total presentation of length more than 500 and this is a presentation less than 100. It's really because the structure of the presentation, it's much simpler. Okay. And more precisely, so this is what I will call a sevenfold generalized triangle group. And I will spend the rest of my talk discussing this notion. And the vertex groups in these triangle groups, I claim that there are 7 groups that all of you know. Okay, maybe you didn't recognize these 7 groups from their presentation, but I will convince you that you knew these groups before. And the reason I gave up the scheme that led me to my older presentation and that encouraged me to find another family of presentations was really the work of this triangle group of people, Alex Olshanskii, Jason Manning, and Henry Wilton. 2 of them are sitting in the front row. And they studied generalized triangle groups, proved a very nice theorem about them. So I will formulate this theorem, but before that, let me step back and recall basic notions. So what is a triangle of groups? That's an old group theoretical notion going back to Neumann in 1953. So I will not define it formally very precisely. Let me say it's a commutative diagram of groups and inclusion maps, as on this picture. You have a group attached to the two-face, to the two-dimensional face of this small simplicial complex. This group embeds in edge groups, and edge groups embed in the vertex groups. Okay, and once you have this amalgam of finite groups, you can look at what in geometry group theory we call the fundamental group, but perhaps Dave Benson would call it the colimit. So it's just the free amalgamated products of all these groups modulo the relations that defined by all the inclusions involved. Is that clear enough? Okay, a special case is when the phase group C is trivial, and well, the edge groups are all cyclic of order k, and in that case, I will say that the fundamental group is a k-fold generalized triangle group.
But what about the vertex group? They can be absolutely...
They will be finite.
Right.
They will be finite.
But any finite group
Yeah.
would be allowed.
Yeah. Special case when k is 2, this is just a triangle Coxeter group. And if PQ are finite, you get a triangle Coxeter group that's a co-compact Fuchsian group. So the classical problem about amalgams of groups is the embedding problem. In geometry group theory, we say the developability problem. So is it true that the vertex groups embed injectively in the colimit, in the fundamental group? And in the case of triangles of finite groups, there is a very famous sufficient condition that gives a positive solution to this embedding problem that I will now recall. And for that, I need to remind you the definition of a coset graph. So here, X, I take it to be a finite group with a generating pair of subgroups, AB. AB will have trivial intersection, they generate X. Okay, and then I attach to this data a coset graph. The vertex set is just the disjoint union of the coset spaces, modulo A and B, and the edge relation is the one you can guess. So you really get a bipartite graph by construction, and it's edge regular because the group X acts regularly on the edges by construction. And I want to attach to this graph what I call the combinatorial angle. It's just 2 pi over t, where t is the girth of the graph. And now here is the sufficient condition for embeddability that I mentioned before. So if I come back to my setup of a generalized triangle group, and the sum of the 3 combinatorial angles attached to the 3 vertex groups is at most pi, then the group is infinite and the vertex groups embed. If the sum of the angles is strictly less than pi, then even more the group G is hyperbolic. So Lubotsky, Manning, Wilton proved the following result. So for every k at least 18, they provided the existence of an infinite family of k-fold generalized triangle groups, Gn, that are all infinite hyperbolic with property T. So in their construction, the vertex groups are L2Qs, with Qn tending to infinity. Peter Varju also has a contribution here motivated by this work that he could show that in fact all large values of k could be taken here. Not so. I think in the original paper, infinitely many values of k were obtained. Varju obtained almost all k. So it was very important for these people that for a fixed k you have an infinite family. Okay, and thanks to this, they managed to answer questions that were asked before. So that's a very nice story. My naive way to look at this is, can you give me one example again? And so if you read their contribution, you find the smallest possible example. I think that's what you have to take for k and q. So this motivates a slightly different question. So what is the smallest k such that there is a k-fold generalized triangle group that is infinite hyperbolic with property T? So k must be at least 3 because k is 2 means we are dealing with Coxeter groups. They never have T if they are infinite. Okay, so let's start with k equals 3. So that's what I want to do. And before I will describe what we did about this case, k equals 3, let me just mention that so the way Alex, Jason, and Henry ensured that their groups have property T is using spectral graph theory. They use a criterion that was developed by André Jouc, relying on the ideas of Garland and Pensu, that says that if the coset graphs that we saw before satisfy a certain spectral criterion, then the group G has property T. This is not the path that I will follow. I want to replace this spectral graph theory business by representation theory. And this is made possible by a very, very nice theory developed by, again, Andrei Hakin and Misha Ershoff. So let me explain this. So again, we start with a finite group X and a generating pair of subgroups A and B. And And now I want to attach another angle to this triple of groups. And I will call it the representation angle. So it's defined as follows. First, fix a complex unitary representation pi v of x. And I assume that this representation has no non-zero invariant vector under x. Now I look at the fixed space of A and the fixed space of B. So these are two subspaces, and I measure the angle. There is one intuitive way to do that. I will not write the formal definition, but it's an exercise for you to write a formal definition of what this angle means, and you will get the correct answer. Okay? And now you take the infimum of all these angles over all complex unitary representations, and it's not difficult to see that actually it suffices to take the infimum over all irreducible representations. So that's the representation angle. So you can check your intuition on a very concrete example. So if you take a dihedral group of order 2R, A and B are the two involutory generators, then without any surprise, so the representation angle is pi over R. It's achieved by the geometric representation on the asymmetries of the R. If you take a group that's a product, direct product of A and B, the representation angle will be pi over 2. So Erschoff-Heiking proved the following amazing theorem, I think. So if you have a group G generated by three subgroups A0, A1, A2, any pair of these subgroups generates a finite group that I call xi, x0, x1, x2. If I can compute the representation angle for each of these three triples of groups, and if I know that the sum of this angle is greater than pi, strictly greater than pi, then G has Kazhdan's property. Okay, so that's what they show. Okay, so to summarize, now coming back to our business of generalized triangle groups, so we take T, our triangular finite group with trivial phase group, edge groups that are cyclic of order k. We have these combinatorial angles attached to the vertex groups. We have the representation angles attached to the vertex groups. If the sum of the combinatorial angles is strictly less than pi, then we know that the group is infinite hyperbolic. If the sum of the representation angles is greater than pi, then the group is property T. So I want to allow the limit cases. So if the sum of the combinatorial angles is pi, I know that the group is infinite, but I don't know whether or not it's hyperbolic. Again, if the sum of the representation angles is lesser than or equal to pi, my criterion is inconclusive, but still the group might have property T. None of these conditions are necessary. And the good news is that there are algorithmic tools that could help here. Of course, if we speak about algorithmic tools, we should remind ourselves that algorithmically, all these questions are undecidable. Hyperbolicity is an algorithmically undecidable property. Why is that? Because of the very simple observation that a group G is finite if and only if G cross Z is hyperbolic. And you know that testing whether a group is finite is undecidable. But nevertheless, algorithmic tools do exist, and so one was developed by Derek Holt in the 90s, and Kolva will speak about a more recent development tomorrow at 1:45. Property T is also algorithmically undecidable because a group G is trivial if and only if the free product of G with the cyclic group of order 2 has property T. Nevertheless, very recently algorithmic tools were developed, and there was a very famous application of these algorithmic tools. They were used to solve positively a long-standing question of whether outer automorphism groups of free groups have a property. And finally, testing whether a group, a finitely presented group, has a quotient in SD is also undecidable. That's a recent work of Wrights and Evans, Liebeck and Seagal, relying on earlier work by Wrightson and Wilton. What's perhaps rather very striking is that, on the other hand, having a finite simple quotient that's not in SD, this is a decidable problem. And moreover, if you restrict to very low rank or very small groups, you do have algorithmic tools implemented. Okay, now, so that's all the preparation. And now I want to describe an empirical study that we performed. So here is the goal of this experiment is to enumerate systematically the smallest possible non-positively curved trivalent generalized triangle groups. Okay. So to do that, we first go through the list of the smallest edge-regular cubic graphs of girth 6 and 8, and there are lists available. There is the Famer-Foster census for the symmetric case, and the semi-symmetric case is more recent work by Marston and his collaborators. So we have to describe the groups acting edge-regularly on these graphs, compute the representation angle, and then once we have all the candidate vertex groups, we have to determine all the ways they can be assembled in an amalgam, and then try to study the properties of all those groups. Okay. So for the cubic graphs of graph 6, we focus on the 6 smallest one, and one of them is not edge regular, so we had to discard it. So we have just 5 cubic graphs. The smallest one is the Hewood graph. The group X is a Frobenius group of order 21, and the cosine of the representation angle is square root 2/3. The next graph on the list is of order 16. The cosine of the representation angle is square root 3/3. And it took me some time to realize that this group X, SL2/3, is actually a complex reflection group whose Cox-Story diagram is that diagram, and this became relevant later. The next graph is the Pappus graph, order 18, attached to the Heisenberg group. The cosine of the angle is square root 3/3. Then we have the Novo graph. The cosine of the angle is square root 4/3. Then we have a graph that does not have a name. Its name in the Foster census. Here the cosine of the angle is a bit more complicated. It's the modulus of 3/13 roots of unity over 3. And then we have the graphs of girth 8. This one is the double cover of the dot decaheron attached to the alternating group of degree 5, square root 5/3. A graph that does not have a name and that does not even have a picture. Square root 6/3. And again, it's a complex reflection group, like the group X here. And finally, the largest graph that we considered is the gray graph of all the 54, square root 6/3. And here, that's very important. So what is the group X this time? It's a group of order 81. It's the 3-Ceylor subgroup in the symplectic group FSP4/F3. And it took me some time to realize that I should have noticed earlier. So that this graph, it's a graph that I knew, because it's a graph that consists, so this 3-Ceylor subgroup in SP4 of F3. So it acts on the spherical building of this Chevalier group, which is a generalized quadrangle of order 3. How does it act? It fixes a chamber in the building, and it acts regularly on the opposite chambers. So this building is a graph, a chamber in that graph is an edge. And so the edges opposite a given chamber in that graph forms itself a graph, which is the gray graph here. Okay? So this is the graph of opposite chambers to a given chamber in that building. Because this graph embeds in the building that's a generalized quadrangle, it is of girth 8. But it is of girth at least 8, but actually exactly 8. But once you analyze this group in that way, you can replace 3 by an arbitrary prime. And look at the P-Silov in S4P. And the coset graph attached to this P-Silov in a natural way will also be this graph of chambers opposite a given chamber, and hence it will be of girth 8 for the same reason. Of course, people had noticed this a long time ago, but yeah. Okay, so once we have these 5 plus 3, so 8 vertex groups, we try to understand in how many ways they can be assembled into a triangle of finite groups. And there are 232 inequivalent ways to assemble them. And we can regroup them according to the girth type of the 3 vertex groups. And it's a rather routine exercise in geometry group theory to solve the isomorphism problem, in the sense that inequivalent amalgams will give rise to non-isomorphic groups in this setting. So one of my motivations to undertake this systematic study was the fact that I knew the 4 smallest groups on this list from before. These 4 smallest groups on this list are the 4 groups that you obtain by assembling, by demanding that the 3 vertex groups are the smallest groups that I described, so the Frobenius group of order 21. And these amalgams had been considered by Ronan in 1984. So, and Ronan introduced them and studied them because he understood that the corresponding colimits act co-compactly, chamber transitively, on an A2 tilde building, each of them. So because they do act on an A2 tilde building, they are not hyperbolic, and they have property T. So that was well known. So other people have studied these groups. So Meixner, Köhler, Wester proved that 2 of them are arithmetic, one in characteristic 0, one in characteristic 2. Much more recently, we understood that the other 2 are not linear over any ring, any commutative ring. But more importantly, so at least the 2 arithmetic ones, they are arithmetic groups of higher rank, and so according to Serre's conjecture on the congruent subgroup property, they should have no finite simple quotients of large rank. Okay, so
going to be residually finite or not?
we conjecture that the 2 nonlinear ones are virtually simple, but we don't know. We don't know whether. Another piece of information that's relevant is that all these groups on the list we considered are related to one another. So the various vertex groups that are described, most of them are non-simple, and there are various maps between the vertex groups, and these yield maps between the corresponding colimits. And that's one of the diagram of epimorphisms that we have. And Jason and Henry pointed out to me yesterday that kernels of these maps could be interesting if one for other reasons. So nothing to say about it. So this is important because property T passes to quotients. Okay, so these groups are less likely to have property T than these ones. And similarly, we are interested in finite simple quotients. So this group will tend to have more finite simple quotients. So what about hyperbolicity? So 149 of these groups are hyperbolic, that follows from the Girth quadrillion that I mentioned before. 4 are definitely not, because they are the Roman groups. And what came to us as a bit of a surprise is that among the 666 groups, 27 of them are hyperbolic, although it does not follow from the Olshanskii result. So this really was something that the computer asserted. And I invite you to tell us something more. What about property T? So for property T, the results we got were a bit disappointing. I mean, we knew that 4 of these groups, the Roman groups, have property T, but they are not hyperbolic. We understood that 12 of these groups do not have property T. And how did we establish this? Because we constructed unbounded isometric actions on the real hyperbolic 3 space and the complex hyperbolic 2 space. And this is where knowing that some of the vertex groups are complex reflection groups became extremely important. For the remaining groups, we don't know whether property T holds. I tend to believe that the only 4 groups with property T on our list are the Roman groups. And these are exactly the groups for which the Hiperbolic criterion applies among all those 3.
So are you able to check the Hiperbolic criterion for all of the others, or is it too difficult?
So
Is it that it doesn't apply, or it's just too hard to
No. So we have all the angles.
You do.
So if you sum up all the angles for all but the 5 Roman groups, you get a sum which is strictly less than pi. So for all but the 4 Roman groups, the Hiperbolic criterion is inconclusive. For 12 of them, we know that they don't have T. What about finite simple quotients, which is perhaps the most important question to investigate, in my opinion? So one of us, and I will not reveal his identity, spent part of his summer break over Christmas to investigate the alternating quotients of these groups in all degrees up to 30 and even up to 40 in quite a few cases. And so this is a very delicate thing to do, certainly for me, especially in degree larger than 13, because in Magma's definition of what a small finite simple group is, the alternating group of degree 14 and higher are big. They are not small, as far as I understand. Okay, so this really requires special abilities. It was very nice that Marston helped. So what did he obtain? So he obtained the following. So for the Girth types 688 and 888, so in most of the cases, what Marston obtained is that usually starting in degree 20, all degrees from 20 to 30 occurred as a quotient. And once this was the case, so this was an incentive to continue investigate larger degrees, and this is exactly what Marston could do, and he could show that all degrees, in most of the cases, up to 40 also occurred. So this prompts me to believe that for these groups, probably almost all alternating groups occur. And the story is completely different for the other Girth types, where some groups have no LD quotients at all, and some have just a few. And now we can speculate about how to do draw a conclusion from this. So what is my conclusion? So this family of groups, I think it's interesting because it interpolates between two extremes. The four Ronan groups that at least conjecturally have no finite simple quotients of large rank, and hyperbolic groups that do not have T and that have a huge supply of finite simple quotients. But in between, there is a lot of space, and some groups seem to have an intermediate behavior. And among all the groups that sit in between, there is this group G3 that I defined before by its presentation. Okay, so let me finish by coming back to this group G3 or GP, where P is an arbitrary odd prime. So what is this group GP? It's a P-fold generalized triangle group. Versus groups are isomorphic to the P-silobs of S3P and the S4P. Okay. So once you know this, you can identify this group with another vocabulary. So it's actually what Erschoff-Reichen called a Kac-Moody-Steinberg group of type described by this Dinkin diagram. But this means that so once you do this identification, some extra bit of information comes up. Namely, you understand that these groups have an infinite Pro-P completion, and also that have infinitely many L3Q quotients. That's moreover, as I said before, we can show property T for all P at least 7 using the Erschoff-Reichen criterion. Okay. So my final sentence is that I need your help, and I want to suggest this as a question for this semester. So I believe that GP is a candidate hyperbolic group with few finite simple quotients of large rank. G of 3 already seems, among the 232 groups that we studied, G of 3 already seems to have fewer quotients than many of his friends. And if you put P at least 7, then as an extra bit of information, you have property T, which is supposed to increase your chance for this term to happen. I'll stop here.
Any questions or comments or assistance for Pierre-Emmanuel?
Is GP Golachef RH?
Golachef, it's, I don't know, I'm not sure.
Could you remind me what L3P and S4P are?
So yeah, so this is PSI3 over FP.
Oh,
And PSP4,
right.
special linear group, dimension 3, and projective symplectic group.
Do you know any quotients for G7?
Yeah, it does have. So
I know it has infinitely many, but
So alternating quotients, we couldn't find any. For G3, Marston found at 27 as a quotient. 27 is the order of the Heisenberg group over F3. So that's the only quotient we found below degree 30. And then what he did was to try 125, degree 125 for G5, and he couldn't find that as a quotient of G5. And for small degree for G5 and G7, he couldn't find any.
But we've got L3 quotient machinery, but not for the number of generators that you're talking about. Can you reduce the number of generators?
Yes, so that's an excellent question. So, for only some of the groups that we have, when the three vertex groups are isomorphic, and when you do the gluings in the proper way, you have a cyclically symmetric presentation. So you can permute cyclically the vertex groups, and this is an automorphism of the presentation, right?
Mm-hmm.
So in those cases, in fact, I have an order 3 extension of my group, and this one is 2 generated.
Right. And what happened with L? Did you run L3 quotient?
Then we did run L3, and we found infinitely many L3 quotients in a few places where we expected it, especially G3. No, not G3 because this doesn't. Especially some of the groups acting on the complex hyperbolic plane. Because these have an action on the complex hyperbolic plane whose isometry group is SU21, which is a subgroup of SF3C. And so these groups have an infinite image representation in SL3C, so we expect to see infinitely many L3 quotients. It's actually a Zariski dense representation, so by strong approximation we expect infinitely many L3 quotients there, and that was confirmed by the L3 quotient. And then there is a bunch of cases where doing what I said, what you suggested, revealed infinitely many L3 quotients that I cannot explain by in geometric terms or by means of an infinite image representation.
Right, well, let's thank Pierre-Emmanuel again for